Hi everybody, I'm the greatest living inventor, and today we are doing my book, What's Wrong with Mathematics and How to Fix It. Okay, which is the initials are what's wrong with mathematics. Okay, so it's WWWM. Okay, and how to fix it. Okay, so I'm not writing anything but the headlines, and I have to do it quick because there are like 30 pages and we have like an hour, so in every 2 minutes we should make a page. Okay, so this is the front picture. Dedicated with love to my father who gave me the power to think big. Did you lose the ring here? No, but the light is much better here. Nasreddin. When I've clarified and exhausted the When I've clarified and exhausted the subject, then I turn away from it in order to go into darkness again. Carl Friedrich Gauss. The mind is sharper and keener in seclusion and uninterrupted solitude. No big laboratory is needed in which to think. Originality thrives in seclusion, free of outside influences beating upon us to cripple the creative mind. Be alone. That is the secret of invention. Be alone. That is when ideas are born. Nikola Tesla. Back cover. Do you think it's a coincidence that only secluded lone wolves like Gregory Perelman and Andrew Wiles come up with amazing breakthroughs? Do you wish the mathematical community could recreate at will the process of happy accidents discovery like the ones by Satyendra Nath Bose, which brought his work with Einstein, and George Dantzig, the real story behind Good Will Hunting? Okay, contents I'm skipping. Okay, preface to this book, What's Wrong with Mathematics, WWWM. Allow me to summarize this book for you, first in 3 paragraphs, then in 6, then in a whole chapter, and then I hope you will read the whole book. In the beginning of the WWM book, I'm using terminology of a detective story. In the WWP book, I'm using medical mystery terms. In this way, I'm hoping to spice up the twin books a little so that you won't notice that WWM is about management and WWWP is about education. Okay, I'm just taking off my jacket. Sorry for the rush. It's the second time I'm recording this and we need to hurry a lot. WWWM in 3 paragraphs. You have just arrived at the scene of the crime. You see mathematics lying on the floor, mediocre but still alive. This was committed recently, more or less in the 1950s. You suspect the criminal is still around. You find the attack weapon, a huge streetlight effect, aka drunkard search. If you don't investigate this case quickly, the mysterious assailant will surely come back and finish the job. Who could have left mathematics so horrifyingly mediocre like this? All your evidence points to the chief criminal working in teams and his accomplice institutionalization. And the dark motive is uncovered, playing safe. In the end of this hair-raising cloak and dagger tale, you will solve the mystery and reveal how they executed their hideous plot, and you will restore peace and quiet to the mathematical community in the following way. Initiating mathematical breakthroughs by allocating each combination of postulates, including hopeless dead ends, to a pair of randomly selected, drafted PhD students. They each work for a half year separately and only then matched anonymously. And for half a year each checks the other mystery man or woman's work. And similarly, methodically trying to connect each combination of mathematical sub-branches, including infertile couplings, like grafting in botany. By the way, all my ideas are taken from the wonderful, really, years I had in Israel's army. WWM in 6 paragraphs. Problem, teamwork. Let's face it. Let's face it. Teams don't function anywhere. There is always someone telling what to do and the rest are doing it. What are the chances that the boss is also the gifted one? In engineering, teams are bad, but not destructive. Someone is doing all the hard work, while the rest are parasites. But in mathematics, teams are so bad they are destructive. Someone comes up with an original idea, and the rest bury it, because a truly original idea sounds crazy at first. I think it's vitally important for them not to work in teams, because teams act like a committee, depressing creativeness and uniqueness and averaging what you are doing. Let's say someone in the team is really ingenious and original. What are the chances that he would also be so dominant in the team that the other members will listen to his original and hard to understand ideas, and the majority will agree to implement his ideas? 0. Original science cannot be discovered through a democratic process, and certainly not by a dictatorship of an old expert who is usually just an expert in politics and affiliating with the right people. Solution 1. Botanical grafting. My idea, but I'm not writing because I will not have time, I'm sorry. Solution 1. Botanical grafting. My idea came from imagining mathematics like a map of some city. There are streets where the mathematicians think there is no entry, although there is no sign saying no entry. It's just that over the years some subjects became entrenched like a paradigm. If we can throw away this paradigm, we can explore some of these new streets and also connect this way areas that were never connected before. In mathematics, such a connection is always great, like for example differential geometry, algebraic geometry, and group theory that connects the whole of mathematics. So, we should try all combinations of 2 existing mathematical sub-branches. In Israel's army, the IDF, they give silly code names to everything, made up of 2 words. Usually one is some random object and the other is some random adjective. Let's say we develop some new weapon, it can be named, for example, Blue Sun. The important thing is for this to be really random. It usually doesn't make any sense, so I suggest systematically pairing up sub-subjects from mathematics and giving them to young mathematicians, let's say PhD students, to explore their connection. The students are not allowed to know each other at any time, and to maximize diversity they are picked randomly by computer. They are drafted for 1 year of their doctoral work as service to mathematics as a whole. All the students' work will be randomly sampled so that they will take it seriously. Solution 2. Planned serendipity. On the contrary, from the Aramaic term in the Talmud, ifcha mistabra. This is a method practiced in the control, bakara, unit of the Israel Intelligence Corps of the IDF ever since the Yom Kippur War, when Israel almost lost because of the concept, a prejudiced strong assumption about how the Arabs must operate. This is the same as devil's advocate or debate team. In a debate team, the sides of the argument are not chosen by the talkers, but are instead being given at random. So many times you argue for a position that you totally don't agree with. I assume the mathematical community is stuck in a concept, much like Israel's intelligence was. For example, this already happened with Euclidean geometry, that the flat plane was considered the only possibility in the parallel postulate. I recommend making a large-scale project of mathematical debates. Of course, it should be over at least a year, and certainly not in real time. Most of the mathematical theorems premises are described in combinations of logical conditions. If this and that and not those, then such and such is true. So I suggest making systematic combinations of negating, flipping, like a no gate. If it's true, then return false. If it's false, then return true. Okay, so combinations of negating each one of these conditions, and again giving each possible version to some other random couple of PhD students to examine what we've got. Okay, chapter 0, summary of the book. Math is stuck in neutral. My claim is that since 1950, all the important advancements were either not in math but in computers, or made by solitary brilliant people who were brave enough to work alone, so they worked in the old way, Gregory Perelman, Andrew Wiles, or made by someone from the old dying generation, Kenkichi Iwasawa of Iwasawa theory. Mathematical workplace. Imagine the following scenario. The team leader, boss, he's the one who has the best people skill, better human interpersonal relationships. He or she made his or her way up through politics, saying mean things behind your back, backstabber toward his colleagues, and flattery toward his boss, brown-noser. This set of skills, humanities, is very different from the set of skills needed to solve the problems, scientific. Even if by some miracle this boss is superhuman and is the best both in science and in people, he will concentrate his energy on the easier path to promotion, which is people. On top of this, there are human shortfalls like bribe, like sexual bribe or donations bribe, or people with connections at high places. The creative team member, worker. Imagine a good-hearted but ill-adapted to society nerd who possibly suffers from Asperger's syndrome, mild disorder on the autism spectrum that makes you good in math. They have trouble to communicate what they want because it's hard for them to see from the other person's perspective. This is the exact opposite of the smooth talker boss type that reaches the higher ranks. Collision between them. You can visually imagine this with the animation in elastic collision. The boss is the big mess and the worker is the small mess. The worker comes up with a brilliant but raw idea and he doesn't know how to market it to the boss. The boss wants something practical and impressive that he can steal and present it as his own idea. If, and it's a big if, the boss can grasp the worker's idea at all, The boss finds it very strange and risky and rejects it forcefully. Chilling effect. Of course, the next time or the next worker will think twice about approaching the boss or even entertaining it in his head, a brain idea. This playing safe from both sides has a destructive effect on the development and especially the research in mathematics. Match made in heaven by the supreme fascist. To understand the enormous potential of matchmaking between two mathematical fields, think of something you use every day, graphs. I mean a graph of a function. For example, a graph in the newspaper of the price of a stock, financial investment over time. A graph is like a snapshot that tells us how the function is behaving. It's so much easier than a table of numbers that we use graphs everywhere, especially in science. Graphs became part of our way of thinking, so much that we take them for granted. But it wasn't always so. The person who married algebra to geometry in this way was René Descartes, which is known today more for his I think therefore I am than for his Cartesian coordinate system. But by inventing this system, Descartes not only thought but also allowed Newton and Leibniz to think up calculus and analysis and to kickstart modern science. Descartes is called the father of analytic geometry, although Fermat also invented it independently. But life is not always fair. Ask Leibniz. Been there, done that? Here is a paragraph from the book Turning Points in the History of Mathematics by Hardy Grant and Israel Kleiner. Here are two paragraphs from the end of the chapter, Analytic Geometry, from the marriage of two fields to the birth of a third. In the 20th century, quote, in the 20th century, such bridge building became enormously important, offering powerful tools to mathematicians. As examples, consider the following disciplines, which by merging two fields lent strength to each: analytic number theory, differential topology, geometric number theory, algebraic topology, algebraic number theory, differential geometry, and algebraic geometry. A grand synthesis, the Lagrange program, relating several areas of mathematics, in particular number theory, algebra, and analysis, was proposed by Robert Langlands. 1936 he was born. In the 1960s, in a series of deep and far-reaching conjectures, some by now established. End quote. This first paragraph says that between the big branches this already have been done. We have seen this was done well when Gregory Perelman answering a topological question with differential geometry, and when Andrew Wiles used the connection between algebraic geometry and analytic number theory to answer a number theory question. This shows that in cases where the basic connection between the branches were made by the best people in the world, such as Henri Poincaré, who in our metaphor knew all the streets of his time, and such as André Weil, who was the best person of his time to connect abstract algebra with number theory. By the way, Yutaka Taniyama thought of the genius idea in 1957, which agrees more or less with my theory. Also, take into account the secluded character of Japan as a culture and Taniyama as a person. Still, I think after the big branches have been connected, now is the time to methodically try to connect their sub-branches. Today, each expert knows only his own field, so we don't have people like the above with insight to naturally connect two branches. So it must be done artificially, like I have suggested. If to achieve this we need two people, one from each specialty, then we need to make sure they are at the same level and not in a master-slave hierarchy. Connecting the main branches is productive, as you can read in Quora in this question. What are some applications in other sciences or engineering of differential topology, differential geometry, algebraic topology, and algebraic geometry? In the good answer by Joseph Hivner. I'm giving you the link. So, above the first paragraph, I'm basically saying it can be done more thoroughly and methodically if it's done systematically in higher resolution of sub-branches. By the way, please notice that all the above people, Russian, French, Japanese, are not Americans. We will soon analyze this factor as well. What about the second paragraph mentioned above, Langlands program? At first glance, this looks like the very thing I'm proposing. And this didn't start yesterday. This program called Langlands program started 50 years ago. So what did they do wrong? A closer look reveals what they did wrong. The people who connected the branches are human. This means that they don't try everything, but only what seems most logical. They don't do absurd things, like entering into a no-entry street. But here we come to another pitfall that the second paragraph fell into. This is an even more serious problem that locks mathematicians in a world of their own. Too much abstraction. I'm just checking the time, 21 minutes 40, okay, it's reasonable. Forgive me for explaining in metaphors, but I am not able to understand subjects like group theory or abstract algebra. Still, I think trends in mathematics are so clearly wrong that we can understand it as a black box without knowing what's inside. To see what programs there are, I found a paper called The Creative Growth of Mathematics by Jean-Paul van Bendegem from the journal Philosophica. Section 3 is called Some Examples of Research Projects and includes the Erlanger program, Langlands program, finite simple groups, probability theory old and new, and category theory. The list also includes Hilbert's program, which is good and doesn't belong. Hilbert posed carefully selected questions on a wide range of topics in mathematics and really focused the mathematicians of his day and the following century, but at the same time didn't dictate at all how to reach the answers. For example, Alan Turing's answer included designing the first theoretical computer. But all the other programs mentioned are bad, because they just take known things and rearrange them, mostly inspired by group theory, and always making things more and more abstract. This is like taking a computer program written in C++ and translating it to Smalltalk just because it's a much more pure and abstract programming language. Or, if you want a non-technical metaphor, it's like translating something to Esperanto because it's more sophisticated. This, of course, creates a lot of secure jobs and lots of work, but what's the use of it being besides making math more obscure and hard to understand, and hence harder to use human intuition for real development? What good is it for the real world? By the way, if your target is not humans but computers, there is sense to do it. For example, Grobner basis from algebraic geometry, which is used in computer algebra. I'm not saying abstraction doesn't have its uses. For example, the person who invented group theory, the tragic genius Évariste Galois, connected field theory and group theory to solve the question why there is no formula for a fifth-degree equation, which baffled everyone for hundreds of years. Or, for example, what Emmy Noether, the mother of abstract algebra, did with invariance when she invented the famous Noether theorem in physics. But we passed this optimum point for how much abstraction do we need a long time ago, and now it's mostly supplying safe jobs for people who are mapping this specific group or that one. What's going on now is people working on what the exact syntax is in Esperanto, when they could express themselves in English, where it's easier to think and progress. Another possible usage for abstraction is recognizing that two things are the same, like in physics, Heisenberg picture and Schrödinger picture, which turned out to be the same. Another example is Edward Witten inventing M-theory and showing that all 5-string theory are the same thing. These efforts should and are being done when they are needed and don't need to occupy the bulk of gifted mathematicians. In fact, you can read in my other book, WWWP, why it's such a waste occupying Witten, the smartest person on the planet, with string theory in the first place. Okay, counter examples. The few counter examples, amazing things that were done after 1950, like Andrew Wild's proof of Fermat-Last theorem and Gregory Perelman's proof of the Poincaré's conjecture, are just making my point stronger. These two people are solitary lone wolves who had to work in isolation and secrecy on their spare time, although they are part of the system. If they were not part of the system, nobody would have read what they wrote. Another counterexample, which turns out to be an example for what I'm saying, is Benoit Mandelbrot, who brought fractal geometry to the mainstream. How did it? He did it after he became an IBM fellow, which means the company IBM let him do whatever he wanted, because they knew there is a chance that he will invent great things. Like Master Oogway said, there are no accidents. The next point will probably alienate most of my readers, but I have to describe the whole truth, and if we are to cure the current condition. Okay, so the dollar chasers. I'll just drink something. The dollar chasers. Americanization of society in general is also to blame. I'm not the first to point that the brilliant futuristic comedy Idiocracy by Mike Judge has since become a documentary. This is especially noticeable in President Donald Trump, who is much worse than President Camacho, because Camacho cared about problems of the people and because Camacho listened to the expert. My original contribution will be to explain how they idiotize mathematics. I claim that just as they are ruining their own country, please read Fast Food Nation by Eric Schlosser, and ruining everybody's world, please read When Corporations Rule the World by David Corten, they are, for the past half a decade or so, destroying science and mathematics. I will now give examples. There is a show on the Discovery Channel on television that demonstrates this. It's called All American Makers. In Israel it's called Invent It Rich. For those who've never seen the show, amateur inventors come to show their prototype products to a cocky rich investor in hope that he will give them money to finish their product, like angel investor or business incubator. On a typical episode it goes something like this. Two products come in. Product A, a mind-blowing, world-saving invention. Like one example that I remember is printer ink that vanishes after a few months, so that the same paper can be used over and over in offices for documents that are not for long term. And so we don't need to cut so many trees in the jungle, etc. Product B, something absolutely useless like a stupid gadget. Like one example that I remember is an app on the cell phone that takes a picture but also records a short video, and later when it scans the photo it shows you a few seconds before and after. The stupid gadget product always wins. The world-saving product always loses. This reminds me of the amazing sentence by Buzz Aldrin. You promised me Mars colonies, instead I got Facebook. This is from Why We Can't Solve Big Problems, MIT Technology Review. This consumerism of everything draws the brightest minds to where the money is, and that is selling a small gadget or feature on the phone that helps to gossip or improve your social status among your peers to millions of idiots worldwide, selling many little cheap things for profit instead of making one big thing that will help humanity. The Cavendish Laboratory. As of 2011, 29 Cavendish researchers have won Nobel Prizes. Here is a paragraph from Wikipedia about the physics department of the lab. Several important early physics discoveries were made here, including the discovery of the electron by J.J. Thomson, 1897, the Townsend discharge, this is how electrical sparks work, by John Seely Townsend, and the development of the cloud chamber, this is how the positron, the muon, and the kaon, K-meson, were later discovered, by C.T.R. Wilson. Ernest Rutherford became director of the Cavendish Laboratory in 1919. Under his leadership, the neutron was discovered by James Chadwick in 1932, and the same year the first experiment to split the nucleus in a fully controlled manner was performed by students working under his direction, John Cockcroft and Ernest Walton. In 1962, John Cockcroft, 1897 to 1967, reflected back on the miraculous year, Annus Mirabilis, of 1932 in the Cavendish Laboratory. Quote, "1 month it was the neutron, another month the transmutation of the light elements, in another the creation of radiation of matter in the form of pairs of positive and negative electrons was made visible to us by Professor Blackett's cloud chamber, with its tracks curled some to the left and some to the right by powerful magnetic fields." End quote. Rutherford reigned over the Cavendish lab from 1919 until his death in 1937. The Cavendish lab in the 1920s and 30s is often cited as the beginning of modern big science. Dozens of researchers worked in teams on interrelated problems, yet much of the work there used simple, inexpensive devices, the sort of things Rutherford is famous for, and the lab had many competitors in Paris, Berlin, and even in the US. How can this be? Good management. First of all, for the sake of full disclosure, they also had good material to work with, as a result of good management of the University of Cambridge. It happened that the crucial year scientifically was also that of an important administrative advance. In 1885, a change was made in the regulations of the university, which had a great influence on the fortunes of the laboratory. This allowed graduates of other universities, and others in exceptional cases, to receive a BA degree after 2 years in residence without taking the normal examinations if they submitted a thesis which was judged of full distinction as a record of original research. At the time, of course, the PhD had not been established as a Cambridge or indeed as a British degree. This new regulation made it worthwhile for people from abroad or from other British universities to come to Cambridge for research, and in particular to the Cavendish Laboratory. The effect was immediate. At the beginning of October 1895, when the regulations came to force, the two men presented themselves almost within the hour at the Cavendish Laboratory. They were Ernest Rutherford from New Zealand and J.E. Townsend from Galway. Later, Wykeham, professor of physics at Oxford. Note, it's interesting to compare this with the end part of my anti-American subsection. Okay, page 15, let's see, minute 34, okay. J.J. Joseph, so two people now, J.J. Joseph John Thomson managed the lab from 1884 to 1919, discoverer of the electron, first M over divided by E measurement. First, to use mass spectrometry. And second, Ernest Rutherford managed the lab from 1919 to 1937. The father of nuclear physics, discoverer of the alpha and beta radioactivity, atomic nucleus, proton, half-life. These two giants stayed out of each other's hair, but even more important, stayed out of their subordinates' hair. Here is a passage of how a visitor from Yale in the USA described the University of Cambridge in England. Department of Physics, the Cavendish Laboratory, JJ and the Cavendish. At the turn of the century, many students were coming from abroad. One of these, Professor Bumstead of Yale, wrote his impressions of the Cavendish Laboratory, where he worked in 1904 to 1905. Quote, "The whole social atmosphere of Cambridge is to an American university man most charming and delightful. Its simplicity and lack of ostentation we have kept over here, possibly as a direct influence. But your social life struck me as much richer and fuller than ours. Really, we seem too busy to enjoy each other's society, and yet we do not get so much done as you. I don't understand it altogether. A laboratory in this country in which nobody worked before 10 a.m. or worked later than 6 in the evening would serve as a terrible example of sloth and indolence. I do not see how you get so much work done and yet have time to live so pleasantly and unhurriedly. We Americans have never discovered that great secret. As for the lab itself, it is difficult to describe the almost paradoxical combination of qualities which I thought I observed there. It is obviously dominated by the personality of JJ, and yet I have never seen a lab in which there seems to be so much independence and so little restraint on the man with ideas. The friendliness and mutual helpfulness of the research students was obvious and one of the finest things about the place, and it appeared to be part of this friendly service to jump into a fellow student if you thought him wrong and prove him wrong. In a good many places, friendship does not stand that strain, but it usually does at the Cavendish. Another thing which struck me as paradoxically fine was the relation between the professor and his students. The great admiration and reliance with which JJ was regarded by everybody was unquestionable. Yet, in matters of detail, there was no subservience. I saw a good many men, while I was there, following their own causes, and I remember well the frank tone prevailing at the meetings of the Cavendish Society, where the prof's theories or experiments were not spared in the general criticisms. Each man working in the Cavendish laboratory had as a rule his own problem and apparatus, a good part of which he had probably made himself. Sometimes, but rather rarely, two men worked together. There was no teamwork in the sense of a group all working on the same apparatus. On the other hand, even when there were 30 men working, each knew more of what the others were doing that would be usual in a modern laboratory. This was partly because the great majority were working on interlocking problems, and it was important to know what results the others were getting." End quote. Note the last words that I highlighted in the last paragraph. No teamwork. By the way, years later, one of the greatest discoveries of all time is wrongly attributed to the Cavendish laboratory, and I mean the discovery of the DNA structure. It belongs to the genius Rosalind Franklin from King's College London. I hope I don't reveal anything new for you here, but still it's important for me to say this. The woman who discovered the DNA structure was Rosalind Elsie Franklin. James Watson, Francis Crick, and Maurice Wilkins are simple thieves. These three thieves stole the Nobel Prize from Franklin, 4 years after her death. Very noble, pun intended. What's more, looking now at Wikipedia, Rosalind discovered another Nobel Prize that was taken by a man, Aaron Klug, 25 years after her death. How come the US, another title, how come the USA didn't collapse yet? Transcription of Dr. Michio Kaku, see links below. I must disagree with my esteemed, so everything is a quote from Dr. Michio Kaku. I must disagree with my esteemed colleague here. First of all, let me say that science is the engine of prosperity, from steam power to electricity, to the laser, to the transistor, to the computer. However, the information revolution has a weakness, and the weakness is precisely the educational system. The United States has the worst educational system known to science. Our graduates compete regularly at the level of third world countries. So how come the scientific establishment of the United States doesn't collapse? If we're producing a generation of dummies, if the stupid index of America keeps rising every year, just watch network television and reality shows, right? How come the scientific establishment of the United States doesn't collapse? Let me tell you something. Some of you may not know this. America has a secret weapon. That secret weapon is the H-1B. Without the H-1B, the scientific establishment of the country would collapse. Forget about Google, forget about Silicon Valley. There would be no Silicon Valley without the H-1B. And you know what the H-1B is? It's the genius visa, okay? You realize that in the United States, 50% of all PhD candidates are foreign-born. At my system, one of the biggest in the United States, 100% of the PhD candidates are foreign-born. The United States is the magnet sucking up all the brains of the world. But now the brains are going back. They're going back to China. They're going back to India. And people say, oh my God, there's a Silicon Valley in India now. Oh my God, there's a Silicon Valley in China. Duh. Where did it come from? It came from the United States. So don't tell me the science isn't the engine of prosperity. You remove the H-1B visa and you collapse the economy. In Wall Street Journal editorial is against a congressman who wanted to ban the H-1B, saying that they'll take jobs away from the American people. The Wall Street Journal said, look, there are no Americans who can take these jobs. These are the highest level of high technology. They don't take away jobs from Americans. They create entire industries. So that's why we have an Achilles heel, and that's the educational system. Again, so sociology majors are not necessarily going to be the ones determining the future of Silicon Valley. But physicists, engineers, we need more of them, not less. I found on YouTube a beautiful time-lapse whiteboard animation of this speech by Dr. Michio Kaku, done by a YouTube channel called After School. If the link doesn't work, search for H-1B Immigration, America's Secret Weapon, Michio Kaku. Of course, you can also watch the original in the channel of the 72 Tube. If the link doesn't work, search for Dr. Michio Kaku, America as a Secret Weapon. Okay, separation from reality. 44 minutes. Separation from reality. Leonard Susskind quoted Richard Feynman, who said, "Physics is to mathematics as sex is to masturbation." End quote. See discussion in wiki quote here. This means that physicists have a partner, reality. This for me resonates very much with another genius, Nikola Tesla, who said, Today's scientists have substituted mathematics for experiment, and they wander off through equation after equation and eventually build a structure which has no relation to reality. This isn't just a feeling. Here is a paragraph from Encyclopedia Britannica that summarizes the 19th century mathematics. I underlined the relevant parts. The growth of mathematics, quote, "The growth of mathematics as a profession was accompanied by a sharpening division between mathematics and the physical sciences, and contact between the two subjects takes place today across a clear professional boundary. One result of this separation has been that mathematics no longer able to rely on its scientific import for its validity, developed markedly higher standards of rigor. It was also freed to develop in directions that had little to do with applicability. Some of these pure creations have turned out to be surprisingly applicable, while the attention to rigor has led to a wholly novel conception of the nature of mathematics and logic. Moreover, many outstanding questions in mathematics yielded to the more conceptual approaches that came into vogue." End quote. I know, now you will tell me about Gödel's incompleteness triumph to logic, about Hardy's mathematician's apology that was proud of not being useful, and about how Hardy's work is useful in some niche in biology, and how our encryption of credit card transactions on the internet is based on the purest of all math branches, number theory. I am aware of this, but all these achievements are just sparse anecdotes compared to what's possible. Look at the pattern. 16th century, people didn't know anything about nature. 17th century, people invented calculus and understood motions of planets, etc. 18th century, people invented differential equations and understood more of nature. 19th century, people invented curved spaces that clear the way for relativity. 20th century, people invent abstract things that are barely useful to life. The next step after differential equations should have been non-linear equations, or something huge of that magnitude. I find it funny that there are two ideas connected to this, and they both have to do with elephants. Elephant in the room. The term refers to a question, problem, solution, or controversial issue which is obvious to everyone who knows about the situation, but which is deliberately ignored because to do otherwise would cause great embarrassment, sadness, or arguments, or is simply taboo. From Wikipedia, underlines by me. Non-elephant animals. Using the term like non-linear science is like referring to the bulk of zoology as the study of non-elephant animals. This is a quote from Stanislav Ulam. What Ulam meant is that 99% of nature is non-linear, like turbulence or the weather, and only 1% is linear. And yet almost all the mathematicians stay away from this. Some hope was rekindled with the introduction of chaos and fractals by Edward Lorenz and Benoit Mandelbrot and others, but unfortunately this was pretty much abandoned, except a cool antenna and image compression that people invented. I think this should have led to work of 99% of mathematicians on this until it's solved. On a large scale, it should have been something like what happened when René Descartes described all the known equations of his time with the graphs he created. We should take all the possible fractals, arrange them, and find a way to translate any given fractal to a non-linear equation. And then smart people like Mitchell Feigenbaum would be able to generalize this more, like in the great book Chaos, Making a New Science by James Gleick. Fractals should have been the new graphs. Okay, fractals should have been the new graphs. If we understood the way fractal graphs are reduced to normal graphs, differential equations graphs, this would bring us closer to reversing the process and finding what is the right equation for a given fractal. Then we could calculate processes that surround us all the time, a dripping tap, a cigarette smoke. We could interpolate fractals, we could intersect them, smooth them, derivative. We could do all the powerful things we do with normal graphs. We should find the equivalence of calculus and differential equations for our non-linear world. Mathematicians in the past century misunderstood what's important. The next step from calculus to differential equations wasn't about making it more abstract. That's just a byproduct. It was about solving more processes that are relevant in science, aka nature and reality. After they took many more steps, but not in the direction that After that, they took many more steps, but not in a direction that contributes anything real. I'm writing more about this in my other twin book, WWWP, in the part about turbulence, including my inventions about the Galton board model and the Strull symbol, an equivalent of the square root of -1 for turbulence. So you are welcome to read more there. Before we conclude the chapter, like Watch Mojo always do, we'll see an honorable mention for the candidates to the chief problem of mathematics in the last few decades. This will not be developed in this book, not because they are less crucial, but because they are already developed some elsewhere. They are already developed elsewhere. Heading: Formalism before intuition. Formalism before intuition. There is a saying in Hebrew from an ancient book called Chapters of the Fathers, chapter 2, verse 5, that is very relevant here. I will translate it for you because the translation in Wikipedia is simply wrong. A kapdan person cannot teach. Kapdan is a word that means meticulous, pedant, strict. Here is the same idea in the context of teaching physics, in an excerpt from the amazing Feynman Lectures on Physics, Chapter 1, Subchapter 1. Now, what should we teach first? Should we teach the correct but unfamiliar law with its strange and difficult conceptual ideas? For example, the theory of relativity, four-dimensional space-time, and so on? Or should we first teach the simple constant mass law, which is only approximate but does not involve such difficult ideas? The first is more exciting, more wonderful, and more fun, but the second is easier to get at first and is a first step to a real understanding of the first idea. On physics, it's obvious that you first teach normal Newtonian physics and only then exotic Einstein relativity. But in mathematics, we do it the other way around. Here is an excerpt from Encyclopedia Britannica. I underlined the relevant parts. Quote, during the 1820s, Augustin Louis Baron Cauchy lectured at the École Polytechnique on the foundations of the calculus. Since its invention, it has been generally agreed that the calculus gave correct answer, but no one had been able to give a satisfactory explanation of why this was so. Cauchy rejected Lagrange's algebraic approach and proved that Lagrange's basic assumption that every function has a power series expansion is in fact false. Newton had suggested a geometric or dynamic basis for calculus, but this ran the risk of introducing a vicious circle when the calculus was applied to mechanical or geometric problems. Cauchy proposed basing the calculus on a sophisticated and difficult interpretation of the idea of 2 points or numbers being arbitrarily close together. Now I'm underlining. Although his students disliked the new approach, and Cauchy was ordered to teach material that the students could actually understand and use, okay, this is the highlighted part, his methods gradually became established and refined to form the core of the modern rigorous calculus, a subject now called mathematical analysis. Traditionally, the calculus had been concerned with two processes of differentiation and integration, and the reciprocal relation that exists between them. Cauchy provided a novel underpinning by stressing the importance of the concept of continuity, which is more basic than either. He showed that once the concept of a continuous function and limit are defined, the concepts of differentiable function and of integrable function can be defined in terms of them. Again, I'm underlining. Unfortunately, neither of these concepts is easy to grasp, and the much needed degree of precision they bring to mathematics has proved difficult to appreciate. Okay, this is the important part. Roughly speaking, a function is continuous at a function is continuous at a point in its domain if small changes in the input around the specific value produce only small changes in the output. End quote. So we are putting a very high doorstep that you have to cross in order to enter calculus, although this is only needed for those who in the future will study some exotic functions. This deters many students from learning all that comes next, because for them this high step is so high that it's like an insurmountable wall. This is even sadder because if the special hard stuff was taught later on, after the students gradually developed intuition with the easy normal stuff, they would be prepared to grasp the hard stuff, because then they would have the necessary context and maturity, and they will even feel they need it to do more advanced stuff. So we are losing each year many potential scientists and engineers and even mathematicians who could contribute other original ideas because they cannot enter the stupid door we designed in the entrance. Of course, this is just an example to a bad process that repeats itself on every stage in math education, where we provide the sophisticated tools to solve the problem before the student tackles on his own the problem that requires the advanced tools. That's why the student feels that every subject in math is hard and abstract and unnecessary. The causality is all wrong. We tend to the exception before the student feels comfortable with the rule. We present the solution before the problem is really bothering the student. We give the answer before the student thought of asking the question. To paraphrase the quote of Jessica Rabbit, math isn't bad, it's just taught that way. I have written a whole book called The Strulovitz System about how mathematics, etc. should be taught, especially for students that struggle. So if you are interested, please read there. Okay, next headline. Mathematics must not be visualized. Mathematics must not be visualized. Here is the beautiful preface from the wonderful book Visual Complex Analysis by Tristan Needham. I'm quoting. A parable. Imagine a society in which the citizens are encouraged, indeed compelled, up to a certain age to read and sometimes write musical notes, musical scores. All quite admirable. However, this society also has a very curious, few remember how it all started, and disturbing law. music must never be listened to or performed. Though its importance is universally acknowledged, for some reason music is not widely appreciated in this society. To be sure, professors still excitedly pore over the great works of Bach and Wagner and the rest, and they do their utmost to communicate to their students the beautiful meaning of what they find there. But they still become tongue-tied when brashly asked the question, what's the point of all this? In this parable, it was patently unfair and irrational to have a law forbidding would-be music students from experiencing and understanding the subject directly through sonic intuition. But in our society of mathematicians, we have such a law. It is not a written law, but those who flout it may yet prosper. It's not a written law, and those who flout it may yet prosper, but it says mathematics must not be visualized. More likely than not, when one opens a random modern mathematics text on a random subject, one is confronted by abstract symbolic reasoning that is divorced from one's sensory experience of the world, despite the fact that the very phenomena one is studying were often discovered by appealing to geometric and perhaps physical intuition. By appealing to geometric and perhaps physical intuition. This reflects the fact that steadily over the last 100 years, the honor of visual reasoning in mathematics have been besmirched. Although the great mathematicians have always been oblivious to such fashions, it is only recently that the mathematician in the street has picked up the gauntlet on behalf of geometry. I heartily recommend to, this is the end quote, now me, I heartily recommend to read the rest of his book. By the way, his preface goes on to discuss the use of computers and how Newton's Principia, which is very different from how we study calculus today, inspired the author. Okay, chapter 1, the problem, like this is non-edited stuff, but I'm reading it anyway. Chapter 1, the problem, math doesn't go anywhere. I claim that mathematics has reached an impasse, a situation where no progress can be made, like a stalemate in chess. Chapter 2, the culprit 1, institutionalization, suits and teams. Chapter 3, the culprit 2, false dead ends. Chapter 4, the culprit 3, the cathedral and the bazaar. Chapter 3, the solution. What happened? How did we come to this? Okay, this is because I don't have an editor. This is how my books look like parts that don't link. Okay, so preface to my twin books. I don't have time to read it, so I will leave it out. Okay, I'm skipping to. I will read it like in another video, because I don't want the video not to record. Okay, so this was my What's Wrong with Mathematics and How to Fix It book, and I'll see you in my next book. So thank you very much. Bye bye.